Today's Energy Leader webinar series is on the fundamentals of the power grid and electricity pricing. Today's presenter is David Ulmer. David graduated from the Pennsylvania State University with a bachelor's degree in Management Science and Information Systems. He started his career as a consultant with Accenture in the Philadelphia area, and he was working hand in hand with clients to implement technology solutions to enhance their businesses. One of David's clients was PJM Interconnection, an electricity grid operator responsible for the reliable and efficient delivery of electricity in 13 states and the District of Columbia. David then joined PJM full-time and began developing solutions to support PJM's real-time grid management and the operation of PJM's electricity markets, the largest wholesale electricity markets in the world. During his over 10-year tenure with PJM, David was the project manager for several large-scale technology projects. He managed an energy management system project team that spanned 3 continents and developed a revolutionary infrastructure to improve the performance and maintenance of grid-scale EMS systems. So he has a lot of experience in this area, and that's why we asked him to present today. David joined EnergyCap in 2013 after being certified as a project management professional by the Project Management Institute. He's a member of the EnergyCap Implementation Solutions team and assists clients in successfully implementing EnergyCap within their organizations. So with that, I turn it over to David Ulmer.
Thanks, John. Well, good afternoon, everyone. As John mentioned, my name is Dave Ulmer, and I've had the opportunity to work in a field that's really excited me. I really get passionate when I start to talk about the electric industry and how it works and some of the behind the scenes that most people never talk about. To be truthful, I've given presentations like this in terms of background in the electric industry a number of times, but I have to admit that this is my very first time doing it as a webinar, knowing that my audience is going to be completely silent. I'm going to have no feedback along the way. So please bear with me as I go through this without necessarily the back and forth that I'm used to. But I hope that you find this topic interesting and take home some opportunities for savings for your organization, as well as maybe some interesting tips that you can take home to some of your friends and family as well. Wanted to start with a quote, and maybe this is similar to your own personal view of electricity in the past. Quote says, "We believe that electricity exists because the electric company keeps sending us bills for it, but we can't really figure out how it travels inside the wires." Well, this quote is attributed to maybe a more well-known Dave than myself. That's Dave Barry, the author and columnist, and some would say a comedian as well. So, but maybe that's your view of electricity. You know that it exists, you know you use it, but you don't really know how it all works behind the scenes. Well, hopefully we'll demystify some of those ideas for you today. A little bit about myself. John gave a good introduction. Just to give you a little bit of my experience working with PJM Interconnection, I did work in the IT division and as a project manager both in the IT division and in the business services divisions of PJM, supporting grid operations and markets and planning. I worked on an energy management system that was really revolutionary. I also had the privilege of working on a smart grid deployment, deploying synchrophaser devices throughout PJM's territory. I also spent several years working in international relations and had the opportunity to meet with organizations around the world and share best practices and learn about the similarities and differences between things in the United States and how grid operations work in other locations. I also was able to work in the member support services area as the manager of that group, overseeing issues through PJM's stakeholder process, including issues of continual market design, new markets, and market products. So with that, let's dive into our topic for today. Understanding the power grid and electricity markets can really save you money. And we're going to answer a couple of questions for you today. Number one, what is the grid and who keeps it running? Why do we have wholesale electricity markets and how do they affect you personally in your organization? And where does the money go when you pay your electricity bill? I find that there are few people who really understand how the grid works and even fewer who understand electricity markets. So we're going to start with what is the grid and who keeps it running. So first off, what is the power grid? When we talk about the term power grid, really what we're talking about is the high voltage transmission system. One way we used to describe it is we're not talking about any of those wooden telephone or electric poles that you see outside your house. We're talking about the bulk electric system. Steel towers, really the backbone of electricity distribution around the world. The power grid transports large volumes of electricity from the generating plants, wherever they're located, to the users, the consumers, commercial industry, etc. Every generator and every utility company that is connected to the grid is fully connected and synchronized at all times. We're not talking about lots of different branches, even though there are many different utility companies, hundreds of utility companies in the United States. They are fully interconnected, and every generator that is connected to the grid is completely synchronized. In fact, in the United States, all of the generators rotate at a revolution of 60 cycles per second, and that's very precise. There's very little tolerance for deviation from that. So every single generator is rotating in complete synchronization, whether it's in Florida or it's somewhere in Ontario. It's completely synchronized one with the other. And that's a concept that not many people realize. What we call that synchronization, or the speed of the electric grid, is the frequency. So how frequently are the revolutions occurring? And as I mentioned, in the United States and in Canada as well, that happens at 60 cycles per second. In fact, if you look across North America, we really have three large grids. Everything you see here in blue or red or green is completely synchronized, as I mentioned. Every generator, every utility company. In fact, if you look just at the eastern part of the United States, the eastern interconnection, which is what we call the power grid, everything east of the Rockies and north of Texas, the eastern interconnection is actually the largest motor in the entire world. Because you think about all of that interconnected equipment, it's really the largest motor in the world. So why do we have three grids? Why are they divided the way they are? Well, the eastern interconnection and the western interconnection are divided by the Rocky Mountains. There's really very little opportunity to connect over the mountains in a very reliable and efficient manner. So instead of trying to tie the two systems together, we run two separate systems, east of the Rockies, west of the Rockies. And then if you look at Texas, you have ERCOT, which is the Electricity Reliability Council of Texas. ERCOT exists as a separate entity really for regulation purposes. The Texas regulators wanted to keep their rights within the state, and they knew that interconnecting across state borders would subject them to being regulated by the federal government. So because of that, they have their own grid in Texas. Now, there are some ties between these systems, but they are not synchronous ties. They're what we call DC or direct current ties. But within each of the colors, everything is completely synchronized. And any action that occurs within one of those grids is felt by every other organization within the grid. So if you lose a generator in Florida, for instance, we had an incident a couple years ago where there was a problem with a substation in Florida. The ripple of that is felt all the way through that entire eastern interconnection. So how do we really get the power from the generator to the home? Well, in this example that I have here, we've got a couple of different power sources. We have a renewable source here, hydroelectric power. We have wind turbines, and we also have what we would call more traditional generation, or in this case, a nuclear generator. In each situation, the generators don't supply their power directly to residential customers, even if they're very nearby. Instead, the output of those generators goes through what we call a transformer or a substation, where it's going to be converted into a high voltage transmission or high voltage electricity to travel across the high voltage transmission system. Well, why do we do that? Why do we do that instead of just connecting residential customers to generators? Well, it's really about efficiency. When you convert electricity and you put it on a higher voltage, you have fewer losses, which are losses of electricity due to heat, so it performs much more efficiently. It's also easier to transport over long distances. So what you have is an up conversion from the voltage that's coming out of the generator onto these high voltage transmission lines. Everything that we've talked about from the generators through the conversion onto the high voltage transmission system is managed by a grid operator. There are several of them across North America, but those grid operators are looking at what the output of the generators, they're looking at the status of equipment, they're looking at the transmission lines, and they're trying to operate that reliably and as cost effective as possible. Then what happens after the electricity has been transported for the long distances, when we get to short distances, it's converted down to lower voltages. And that conversion process then allows it to be transported on those wooden poles, down your street, and eventually to your home or business. And that electricity, when it arrives at your outlet, it has been down converted to the point where it's only at about 110 volts in your outlet, as opposed to the high voltage transmission system, which in the United States goes up to 768 kilovolts on the system. So you can see there's a large difference between the voltage on the high voltage transmission system and the voltage that arrives at your home or your business. Anything that's prior to that down conversion, again, is managed by the grid operator. Anything on the other side is managed by the local distribution company that you would pay your typical bill to. So who regulates the grid? The Federal Energy Regulatory Commission, or FERC, is responsible for interstate trade of energy. So that their responsibilities include the electric grid. It also includes natural gas transportation across state borders as well. So all grid operators and companies that transact across states have to have their tariffs approved by the Federal Energy Regulatory Commission. Same for generation companies as well. They're really looking to ensure that everything is fair across state lines. When you get within a particular state, then you have regulations that are typically managed by a state public utility commission. They are focused on setting rates for the consumers. What are consistent and fair rates for consumers to pay within their particular state? Here within Pennsylvania, we have the Pennsylvania Public Utility Commission. That's their responsibility. So you have, in some cases, two different jurisdictions that are responsible for the trade of electricity, but once it crosses state borders, you always have the Federal Energy Regulatory Commission involved, and their offices are in Washington, D.C. As we look across North America, there are several, I mentioned there are several grid operators. I've listed the largest ones here. In fact, the FERC, or the Federal Energy Regulatory Commission, in 1996 issued Order 888, which helped to break apart monopoly utilities, where there were companies that owned the generation, they owned the transmission lines, and ultimately they served the customers all the way at their homes. Order 888 helped break that apart and really establish a network of independent system operators. And it's at that point in time that FERC established this term, ISOs, Independent System Operators. An independent system operator is an organization that does not own any assets of the grid. They are simply there to help manage. In some cases, you might compare them to the FAA, or if you think about the air traffic controllers who are thinking about managing all the planes, managing the skies in a fair and efficient manner, but they don't own any of the equipment. Well, that would be an independent system operator on the electric grid. And I've listed a few of those here. After those got established, FERC expanded some of the definition for what those types of organizations could do. And in fact, they created another term, which is Regional Transmission Organization. In some cases, you can think of an ISO as being a bachelor's degree and an RTO as being a master's degree. Every RTO has requirements that are above and beyond the requirements of an ISO. For instance, an RTO has additional grid reliability services that they offer in terms of ancillary services, which we'll talk about in a little bit. RTOs are also focused on planning for the future. They're not just looking at opening the grid so that it can be used by multiple players, they're also looking to the future and making sure that the grid is continuing to grow and change as it's needed to support the infrastructure of the country. If we look at what happens on a constant basis, there's this tension or this push and pull between the resources that are adding power to the grid and those resources that are taking power off of the grid. We really don't have a lot of options for electricity storage. So this balance must be constantly kept between generation or imports and those resources that are using electricity. The analogy I like to use is think about a bathtub. You have a bathtub, but instead of a typical bathtub, imagine that the drain on your bathtub can be closed or opened. You've got a lever that can change it. And that bathtub represents the status of the electric grid. When you close that drain, you're using less electricity. Therefore, you don't need as much water being poured into the tub to maintain a constant level. So that drain represents everything that's pulling resources off the grid. It's people using electricity. It's exports. It's also losses on the system. If you want to keep your bathtub at a constant level, then you have to constantly change the amount of input, the amount of generation that goes into that bathtub to always match however much is being drained out on the other end. Anytime you have generation that you're adding to the mix, your frequency or the speed at which all those motors and generators are turning goes up. Anytime you use electricity, it's slowing down that frequency. So that's why we say we keep the frequency in a very close tolerance to 60. It might go slightly above, slightly below, but you don't want it to swing way above or way below, because that means you're not managing that balance between what you're generating and what you're using on the system. So this is an actual graph from last week that I pulled from one of PJM's systems. And this shows what they're seeing on the grid all the time. Anytime that you see the chart go above the black line, that means we're overproducing generation. We are overproducing the amount of electricity compared with what's being used on the system. Anytime you see something dip below the black line, that means that there's more power being used than what's being generated. And the grid operators are constantly reacting to try to keep as close to that center line as possible. So we've covered a little bit of what is the grid and who keeps it running. Let's talk now a little bit about electricity markets and their effect that they have on each of you. So how do we calculate the cost of electricity? Well, in the past, before some of the changes that the FERC implemented, the prices were set by the utility companies, and a lot of them were set as cost recovery. So the more that they spent on infrastructure, on generators, on producing electricity, the more return they got, because often those returns were flat rate returns. So the more you spend, the more you return. Well, you can see where there's a problem with that model, because from a consumer's perspective, they have little to no control over what's going on the grid and how they can save money. So the FERC has changed that, and they've encouraged independent generation offers. They've tried to take the risk of building generators off the consumers and place it onto investor-owned companies. In fact, if you look at organizations like Exelon, a very large utility company in the United States, they own generators, they own transmission lines, and they have distribution companies that distribute to end consumers. The FERC requires those types of organizations to have barriers within their companies. So they are not allowed to share information between their generation portfolio and the side of their company that's buying power, or the part of their company that is transmitting the power. They have to have divides within their organization to ensure that everyone who uses the grid is treated fairly and doesn't have an advantage one over another. And that's really where the competition comes into play, because as the generators compete, that drives down the cost of electricity for consumers. So let's see how it's done with a real-world example. What I have here depicted in the black line, the dark black line, is a load curve for a day. And what that means is that as we go throughout the day, from the beginning of the day till the end of the day, we can see how much electricity is being used, starting here close to 100,000 megawatts, dipping down and then heading back up and then back down in the evening. So what a grid operator would do is they would look at this and they would forecast this in advance. And they would say, okay, what do we anticipate tomorrow to look like? And then let's take the offers that we've received from generators and let's stack those up from our cheapest generator all the way up to our most expensive generator. And we will select generators based on how inexpensive they are and use up the least expensive generators first. So for the majority of the day, we're not using any resources that are $100 or more. It's only for a limited part of the day that we have to even tap in to those types of generators. So in that way, the consumers benefit because they're paying for the least cost generation for the majority of the day. When we talk about prices, there's a term that's really important to wholesale electricity prices, and that's the locational marginal price. It would be nice if it were easy to say that we could just stack up generation like this every day and use it. But in fact, we have to also consider where the generation is located. So we have to take the energy price that would exist without any constraints, without thinking about the fact that we do have limited transmission lines and we do have a physical system that we have to maintain. We take what that price would be without limitations, and then we add to it additional charges based on how difficult it may be to get electricity from a generator or into a particular area within the country. We also have to add the cost of any losses. If we have to produce an extra megawatt of power because we're losing it during transportation, we have to bake that into the cost. And as a result, generators are paid based on how available their electricity is to the rest of the grid. Likewise, customers should pay based on how easy it is for the grid companies to get power to them. If they're in a very remote location where it's very difficult and it costs a lot more to get electricity to them, then the electricity costs in that area should reflect that difficulty. As a result, the prices on the electric grid are dynamic. They change up to every 5 minutes based on which generators are producing, what are the losses on the system, how difficult is it to get power from one part of the country to another. Graphically, this is what it looks like. This is a picture taken from the Mid-Continent ISO, and they're pricing for a particular moment in time on the electric grid. The colors represent a variety of different prices. As you can see, prices in some areas are very low. In fact, they may be negative, which we'll talk about in a second, which is right here in the middle. In other parts of the system, the prices are quite high. If you look here in western Kentucky or the southern part of Illinois, the prices are much higher. That's based on which generators could be used and how difficult was it at this moment in time to get electricity into a particular portion of the system. In fact, you'll notice that there's almost a vertical line right here with much higher prices in the east than on the west. That's most likely due to transmission lines that are getting close to overloaded, and cheap generation on this side of the line just can't flow anymore to the east, and as a result, more expensive generators are turned on the east side, causing the prices to be more expensive for consumers on the eastern side of that transmission line. Another example from Superstorm Sandy. This is from PJM's territory. In this particular case, Superstorm Sandy hit the Northeast, and in fact, it blacked out portions of Pennsylvania and New Jersey. As a result, prices in that part of the grid went negative. And the reason they went negative is because there are certain generators that may not have been able to supply load in their area. But those generators are very costly to turn off. They may be nuclear generators or large coal generators that if they're turned off may take several days to turn back on. So it is more efficient to pay people, to have more incentive for people to use electricity in that area than it would be to turn off those particular generators. So negative prices do exist on the grid, even if we don't see them in our retail bills. So what influences electricity prices? We've talked about The location can have an influence, but the biggest two influences on electricity prices are really weather and human behavior. So if we look at these two charts are meant to represent a typical summer load curve, how much electricity is being used in the summer versus how electricity is being used in the winter. And you'll notice that these scales are not the same. The peak here is closer to 150,000 megawatts, whereas here it's only about 100,000 megawatts. So the curves are very different. In the summertime, there's a more gentle increase of electricity usage during the day as things warm up, as more air conditioning is turned on. In the wintertime, instead, we see a very steep change in electricity usage in the morning when people are turning on lights, when heating systems are turning on. This is very difficult for a grid operator to manage. But then during the day, once buildings have heated up, there's a gradual decline in electricity usage. But then as people go home at night, another peak, both in terms of lighting and heating, that occurs at the residential level. So this is human behavior mixed with weather that's really changing what a grid operator has to supply to the grid throughout the day. As a result, it's really an art and a science combined. There's the art of forecasting electricity usage, which is something the grid operators do every day, every hour, every minute. They also need to schedule the cheapest generation possible, knowing that not everything's in their control. So they do their best to schedule the resources that can meet the needs as best they can looking into the future. They also have to make sure that at no point in time are they damaging the transmission system, burning down lines, or causing problems that would have a longer effect of the grid. They also have to balance that with reacting to unexpected changes. If, for instance, you have a steel plant that suddenly fires up all of their kilns, they have in that, or their furnaces, in that particular situation, the grid operator has to suddenly react to a huge change in power usage in a very small area of the grid. Those types of changes occur all the time. So when we look at a daily price schedule and what ends up happening on the grid, we see the prices change throughout the day. And in fact, typically, especially if we look at the summertime, the prices really do peak in the afternoon when air conditioning is at its highest and electricity usage is at its highest. Yet there are times during the night where electricity prices are extremely low because we don't need a lot of generators and we can use that inexpensive generation on the grid. The problem is that from a retail perspective, customers don't see those changes in prices. The most you might see is typically an on and an off peak price. But in fact, the price on the grid and the price that your utility companies are having to pay when they buy electricity for you is very volatile. But since you don't see that volatility, you see this flat line, there's very little incentive for you as a consumer or as a business to try to shift your usage from these peak periods to these periods in time when the prices are much lower. Because if you change your behavior, you're not going to see a huge change in your electric bill. This is something that may change in the future as we talk more about smart grid, demand response, price responsive demand. These are topics that we may talk about in a future Energy Leader webinar series. But unfortunately, most consumers don't see those changes in prices throughout the day. They see a flat rate, and they don't know that there are opportunities for them to save money if they could just adjust their electricity usage to a different time of the day. So we talked a little bit about the grid and electricity prices. Now let's talk a little bit about where the money goes when you pay your bill, our final topic for the day. There are other things that grid operators have to worry about other than just making sure that they have enough electricity to match what they forecast demand to be. In fact, when they're looking at supplying enough generation, what happens if they get into a situation where they think it's possible that usage might go higher than the amount of generation we have available? What do they do in those situations? What happens when the human behavior factor comes in and things occur that are different than the normal? Or what happens when there's an equipment failure on the grid? Well, these situations are not handled by the standard energy market or electricity market. Instead, there are additional electricity markets and ancillary services which provide for these particular situations. I will leave this case study here for you to look at if you download the slides, but it talks a little bit about what happened in New England recently when they had a shortage of electricity that they're forecasting into the future. The end result was that even though there was only a slight shortfall in being able to supply power, the cost to the New England area was over $3 billion difference. So because of this small change in resource availability, consumers are going to be impacted in a single year by about $1.5 billion. So we're talking about huge dollar amounts when we get to those situations where we think there might be a shortage on the system, because we want to make sure that there's always electricity available for all users at all times. So the way that that's handled is through capacity markets or capacity charges. Capacity is the ability to ensure that all customers have electricity whenever they want to use it. The grid operators plan for only one controlled blackout every 10 years. That's a statistical number that they use in their calculations to ensure that everybody has the power when they need it. They use forecasting and statistical analysis to determine what future use, meaning use 5 or 3 years into the future, might look like. These capacity charges that we all pay as consumers or as businesses provide a daily revenue stream to ensure that those generators that are used very infrequently but are yet critical to the reliability of the grid, make sure that those generators have this daily revenue stream to stay in business. So another term for capacity is demand charges. If you look at your electricity bill, especially if you look at your businesses, you'll notice that there are demand charges. Those charges go to pay for generators to ensure reliability on those peak days during the year. Here's an example that compares the peak usage at different seasons of the year. And you can see that when we look at April or October, the fall and spring seasons, the usage profile is much lower than what's used in the summertime. But the problem is we can't just plan for what's going to be used in the spring or fall. We have to have generators available all the time to meet those peaks. And in fact, the capacity requirement ends up being based on what is the most or the worst usage day in terms of grid operation for the year, and then add a buffer to it. So the capacity has to be procured higher than the summer peak. But those payments then are spread out to consumers throughout the year. In addition to capacity payments, there are other grid services like regulation, spinning reserves, black start, and reactive services. These are other types of services that grid operators need to have, or tools that they have in their toolbox in order to ensure grid reliability. They refer to how fast generators can respond when there are problems, how much reserve there is available to be called onto the system within 15 minutes, what happens if you have to start the grid up and everything is blacked out, and also how do you sustain voltage on the system at all times. So when you add all of these different services up, what does it look like in terms of your utility bill? This is a sample from PJM that was taken from last year. And at that time, you can see that more than 75%, or about 75% of the cost that's paid by a consumer goes to how much electricity they use. And that makes sense. The more electricity you use, the higher your costs are going to be. But you'll notice that the second highest payment amount goes to capacity or demand charges. As a consumer or a business owner, you can control this capacity charge to some extent. You can look at what are my peak days during the year and realize that those peaks that occur, maybe it's in the summertime, affect your charges throughout the year. If you can curtail your energy usage during those peak days during the year, you can save money on your electric bill all the time. Other services that you're paying for, transmission services, ensuring that the transmission lines are maintained, and then some of these smaller services that we talked about to ensure that the grid can respond in the case of an emergency. So today we've covered a number of topics. We've talked about what the grid is, who keeps it running in terms of the system operators, the reliability, transmission or regional transmission organizations. We've talked about how electricity markets work, how they set prices based on generator prices, and adjust those prices based on location, and that each location on the grid really has a different price based on how easy it is to get electricity to a particular region. And then we've talked about where does the money go. It doesn't just go to pay for the electricity you use, but it also goes to ensure that generators are available all year long, and that's in the form of capacity payments or demand charges on your bill. Those charges also include reactive services or regulation, and also some black start services, some other services that are really required to make sure that you have reliable electricity all the days of the year. I hope that this topic has been interesting to you. I hope it's piqued your interest in terms of how the grid works, thinking about frequency and how everything's interconnected in terms of electricity markets and all of the factors that go into the constantly changing electricity prices. And I hope that you'll join us in the future as we have additional webinars that talk about ways that you can save money on your utility bills, and potentially some additional webinars about demand response and price responsive demand in the future of where the electricity is going based on the infrastructure changes of the smart grid. Thank you for your attention, and with that, I'll turn it back over to John Hines, our VP of Sales.